know how the programming has been evolved and why programming came to existence and why do we need programming and there are a lot of something. These are all something like stories, like a motivation thing. And there is some background information like, yeah, today we are in a complex computer uh, era where we are able to build the complex applications on the ARM chipsets, MIPS, and other chipsets. And yeah, uh, the targeted audience for this session is something like freshers who are less than 2 to 3 years experience or 5 years experience people. And it may look boring for the experienced people, but still, I would like to share my thoughts on this. Yeah, let us go ahead. Yeah, this is the table of contents for my first PPT to give the introduction. So all of you are from circuit branches, right?
I am from computer science.
Okay. So because why I'm asking this question is, I hope all of you will have a subject called digital electronics, microprocessors, and all these things, right?
Yes.
And so if we want to do a better coding on an application in Linux in C and C++, if we have a better understanding of digital electronics, microprocessor, computer architecture, data memory, and code memory, we can do a better coding. I mean, yeah, even without all these concepts, we can code and the code will run without any issues. But when it comes to performance and all, if we have all this knowledge, we can write a better code and even we can write better tools also by using this knowledge. Yeah. Uh, so we all know how the CPU came to existence, right? The SoC. So from I think all of you had a subject called basic electronics or something like that in your colleges, where you had transistors, gates, circuits, and the. I don't think all of you will have the CPU design CPU as a topic or a subject. Okay, the diodes are. This is how the CPU gets evolved. Okay, the diodes are built by Sorry, the gates. When it comes to gates, the gates are built by the transistors and diodes. And yeah, see when you look into I will show you a simple ALU. Okay, this is a simple ALU where it can do addition, subtraction, multiplication, and division. Okay, so uh, it can do some operation. This is actually, if you see the right side of this, you can see some code here, which is written in VHDL. Okay, VHDL is a VLSI design uh, coding. I mean VLSI designing language. So any simple ALU will have these functions. Actually, this is a simple ALU, a 4-bit ALU, where there will be uh, two inputs and we can select the operations like addition, subtraction, multiplication, or division, and it provides the output, the result of the operation. Okay, and when you see this, it is processing the three inputs. Okay, you don't need to understand everything in this. Okay, I'm just telling you how the ALU is designed. Okay, uh, it has the function called process. It has got two inputs, A and B, and there is an operator selection. So I can provide one input A and one input B, and I can give a operator selection like uh, see here 00 is considered as a this is simply looks like a C program, right? Switch case statement. Okay. When there is a 000 in the operator selection, it has got three inputs. Okay, three line data. When it is 000, it is addition. This is how we can design a simple ALU. And finally, output of the ALU is assigned to the. Okay. So what I am trying to tell you is ALU is nothing but set of circuits, digital circuits. Okay. So I think you might have studied addition, subtraction, adder circuit, subtractor circuit, a multiplier and divider. I don't think you'll have in the syllabus. The full adder, half adder circuits you might have. Okay. What I'm trying to tell you here is the ALU is nothing but the set of circuits, digital circuits, which does some operation on the inputs and which gives the results. Okay, so uh, yeah, this circuit is nothing but it is built by gates. Okay, logic gates. And how the gates are manufactured? The gates are manufactured by using transistors. Okay, this is my mistake. Okay, transistor should come here. The diode should go here. Okay, transistors are made up of diode, not diodes are made up of transistors. I will correct this. Okay, so what I'm trying to tell you is this ALU is made up of simple circuits and also, yeah, it's very complex. But if I want to visualize as a simple concept, I will visualize as a simple four operation ALU and it does some operations. Okay. So here, the ALU is nothing but ALU or a CPU is nothing but it's built by the digital circuits. Okay. And again, the digital circuits are made up of transistors. Okay, so if I modify, so the transistors are the building blocks of the all the CPUs, SoCs, and whatever the things, whatever the digital CPUs you see, they are made up of transistors. So if I make a smallest transistor, like you heard of the technology like 9 nanometer, 10 nanometer, 60 nanometer chip and 40 nanometer chip and all these, right? And this 40 nanometer, 20 nanometer, 10 nanometer is nothing but the gate length. Transistor consists of gate uh, and other two, collector and emitter, okay? Oh, so the gate channel will take the more space, okay? So as I reduce the gate size, I can reduce the size of the transistor and I can put lot of transistor in a smaller area. So I can build more and more circuits in a smaller area. Okay. So as we can manufacture smaller and smaller transistor, it gives rise to a complex CPU because I can put lot of intelligence within a smaller area. So this is how the CPU get evolved. Earlier, they had a 200 nanometer chipset, 150 nanometer chipset, because the technology was not developed. But these days, the companies like Intel, AMD, and all, they came up with a technology where they can operate on nanometer lens. So they are able to build the smallest gates, and they are able to come up with the complex CPUs within a complex CPU, which is very small. Okay. So if you see this, yeah. Uh, so as the days goes by, from last 15 to 20 years, the main modification was done in the transistor length. That this is called as the technology growth. That the transistor technology variation is called as the technology growth. So they started building the smallest transistors and which give rise to the complex CPUs. Okay, the complex CPUs and SoCs. So that they can process lot of data or lot of complex operations in the smallest area. Okay, this we can call it as the intelligent density. Okay, oh, this we can call it as intelligence. Intelligence density is nothing but intelligence per area. Transistors are the intelligent people, so intelligent devices. So as many transistors we can embed, it give rise to the more things. Have you heard of Moore's law? Moore's law states that uh, the transistor see the y-axis says the transistor count, the x-axis says the year actually, the year of the evolution. So as the days pass by, as the year get evolved, the number of the transistor is count is increasing on a chip. So it means I can embed lot of transistor in a smaller area, and uh, I can embed more and more intelligence in a smaller area. So the cost of the intelligence gets reduced. Okay, but it is abundantly available. So when it comes to the programming language, if you see this slide, okay, if you see this slide, uh, when I select triple zero, it is doing the addition. When I select 001, it does the subtraction. This is nothing but a switch case statement in this looks similar to switch case statement in the C program. Okay, So if I want to, so how you can program this is, how we can automate this is, uh, second, I'm going to another slide. Yeah, here with respect to this smaller CPU, the CPU has got nothing but a few operations, inputs and outputs. Okay, the operations are nothing but 3-bit binary numbers, and inputs are 2-bit binary numbers, and outputs are again 3-bit binary numbers. If I want to code this, uh, nobody can understand. Okay, that's how the compiler got arised. The compilers, they build the compilers to convert the human readable machine code, human readable code into the machine code where machine can understand, and finally it is executed on the hardware. So this is how the compilers, coding, and all this came into the picture. So I think the first CPU designed is IN4004 by Intel. It was a 4-bit CPU, and it was very simple. I don't think the compiler was there at that point of time. Okay. So if you see this,
Yeah. Sorry to interrupt you.
yeah.
So earlier, even before the 4-bit computers came into picture,
Okay.
there was a concept of 1-bit machines.
Okay.
Okay. This was the reason why we don't find any documentation related to this is because most of these 1-bit machines were used in defense applications.
Okay.
Okay. So the first computer which was developed was like a 1-bit machine. They were using a combination of 4 to 8 bits, which were we usually called it as a 1-bit machine, and a combination of these machines were used in defense applications.
Okay.
And coming to the size of the transistor, currently we are in earlier we were in a technology where it was measured in terms of hundreds of nanometer.
Yeah.
Okay, but today we are at 5 nanometer technology, and we have saturated ourselves. Okay, so
Okay.
Moore's law was applicable only till I think 2017 or 2019, where it clearly says that the number of transistors on a chip doubles every year.
Okay.
So whatever processor you had in 2016 and whatever processor you had in 2017, the number of transistors were double. Okay, but now after the 5 nanometer technology, we are in a stage where we are stuck in a position where you cannot go below 5 nanometer. Okay.
Okay. There are some
Because
limitations you mean to say,
there
Shiva?
are, yes, there are hardware limitations at atomic levels.
Okay.
And the cost of production for a less than 5 nanometer chipset is quite high. So
Okay.
that's why the 5 nanometers chipsets are the kind of, at least from past 3 years, the 5 nanometer chipsets are a standard. And if we have to go below 5 nanometer, we have to use the carbon nanotube technologies.
Okay.
Okay, which is still in the research phase. Okay, so this is all some additional information apart from what Chandra has in his slides.
Okay.
Okay,
Shiva,
so yeah,
sometimes I remember one of my professor told there were some research going on carbon nanotubes in
yes,
ASC Bangalore.
yes. IISc Bangalore has been one of the biggest contributors for the carbon nanotube technology, which will probably be equivalent to 1 nanometer. If you have to compare it with your normal chipset, it's going to be like kind of 1 nanometer chipset or lesser. But the problem with carbon nanotube technology is that it is quite expensive. That is also one of the reasons why we have not adapted it to the user-based applications.
Okay.
Okay. Those were
Okay.
the two things which I wanted to bring in additional to whatever is there. Yeah, you can continue, Chandra.
Yeah, guys, actually, this is what the story behind the programming languages and the era of the new CPUs and how a CPU will be organized at the very simplest way. Uh, okay, and yeah, I think we already know about all these things. This is fine to go ahead. Uh, I think you are
So
all. Yeah.
anybody who doesn't understand the general microprocessor architecture? Okay, yeah, we can go ahead.
Okay. Yeah, normally any microprocessor or any microcontroller, it will have ALU, arithmetic logic unit, and the internal registers, and an externally interfaced RAM. Okay, and yeah, registers are very useful. See, why I am telling you is registers keep some of the data. Okay, I cannot keep the data in the RAM always because it takes a lot of time to access the data. If I do any operations, I mean, if I want to achieve the operations in a faster way, every time I cannot go to the RAM and fetch the data and bring it to the ALU and do it. So they designed the uh, uh, simplest, I mean, the low size memory, which is 8-bit, 16-bit, and 32-bit registers, which is that will store the data. And RAM can store even the data and the code. We have seen, right, when we do malloc, the it's a data memory actually, which will be allocated from the RAM, which is heap. Okay, so RAM is compatible with both the data and code, and the CPU will have internally, it will have registers and cache. Okay, this is about data memory and code memory. And yeah, so coming to the automation and programming languages, see, we can achieve the automation. How these things are required actually, controlling the flow of automation. Like I need, I need to compare the data with some values. Depending on some condition, I need to take some decision, or and yeah, for that actually some controlling structures are required in any programming languages, which includes if else or some elements like that. Okay, processing actually, yeah, there's nothing but operations. To do operations, they will have the program, the any programming language. It will have its own inbuilt functions or the instructions to the process. The repeatings are nothing but the loops. Okay, so if I want to repeat something for 100 times, I don't need to write the 100 lines of code which executes, because it increases the size of the code, and we can have a simple instruction which gets repeated for 10 or 20 or depending on the user requirement. So, and one more thing is, yeah, sharing the code across multiple applications. So if each and every application has got its own code and which is not shared across. If you see Linux system, you have seen the user lib directory, right? User lib or lib directory, where we will have the .so files. So those .so files are nothing but the shared libraries which are shared across multiple applications. They will be loaded at the runtime. Okay. So code sharing reduces the memory footprint of the applications or the system. Okay. That's how the shared libraries came into picture. When it comes to parallelizing, yeah, it is something like, for example, consider I am playing a YouTube video, okay, on a mobile phone. So in that case, it is something like the mobile phone the system has to download the video and then decode the video, separate the audio data and video data, send the audio data into a speaker, send the video data into a display device, and then that too video should be there with higher frames per second. Otherwise, video will look like a slideshow to any human. So it should be 30 frames per second. You can see so much of things going on uh, in a simple YouTube player application, right? So in this parallelizing is required. Yeah. Uh, for example, we can have one thread which will download the YouTube data, and another thread which will take the downloaded data from the system and then it decodes, it separates audio and video data. Another thread which copies the data from that thread and puts it into the display device and audio device. So these are some of the, this is why the parallelizing is required. So these are some of the basic components which are required for any programming language. So any doubts, guys? Like, these are very basics actually. I just wanted to go through all these things before we start some training. Yeah, I assume you don't